So welcome to this talk about enumerated types, type extensions and defaults for MiniZinc. So what are enumerated types? Well, these are in almost every programming and modeling language. They allow us to give a named set of entities. So in MiniZinc format, we can introduce a color enumerated type which has red, blue and green, has 3 different colors. Or we can have anonymous enumerated types. So here we've got enumerated type position, which has 3 unnamed positions. And they're useful because they give a better documentation of the model, but they're also important for type safety of models. So here's a simple kind of knapsack problem. We've got to pick k products out of n. We have to make sure that they're all different. So we're picking, the decisions are these chosen products. We have to choose different ones. We have to make sure that the sum of the prices of the ones we choose is less than or equal to the budget, and we're trying to maximize the profit that we get. So this model works. It will give us answers. Let's rewrite the model using enumerated types. So obviously the product, rather than using numbers 1 to n, we should use a enumerated type for the product. Nothing else has changed, but something has changed. This model fails to compile because there's a type error here, right? So when we tried to maximize the profit, we had profit of I, but we should have set profit of chosen of I. And the type error has been detected by the compiler, and so we're going to fix that before we try and run the model. And so that bug can be very hard to detect, because we're using integers for multiple things and we use the wrong integers in the wrong places. So enumerated types have been in MiniZinc for a long time, and in other languages they're very useful. But sometimes we end up using integers even though we'd like to use an enumerated type. So here's a small part of a pizza voucher problem where we've got to buy a whole set of pizzas and we've got these vouchers saying like you can get 2 pizzas for free. If you buy 2 pizzas, you get 1 for free, right? And so these key decisions for each pizza is how do we obtain the pizza? We can get it for free using voucher j. We record that using -j, the integer. We can just buy it by itself. We use 0 to represent how we got it, and that's the case. Or we can use it to enable a voucher. So if, let's say, voucher 2 requires 2 pizzas to get 1 for free, then we need 2 pizzas with how of 2 plus 2, meaning we enable the voucher and then we can get 1 pizza with how of -2, which we get for free. And one of the key constraints in the model is that for any 2 pizzas, if we use one to buy a voucher and we get another one for free, then the one we use to buy has to be more expensive than the one that we bought. And that's modeled here. We basically say, well, they're both working on the same voucher because the voucher, this number is negative of each other, and how of P1 is greater than 0, so we used it to buy the voucher. And therefore, price of P1 is greater than the price of P2. So here's the version using enumerated types. So what have we changed? Well, rather than using 1 to n to represent the vouchers, we're using anonymous enumerated types, so we're going to get better type safety there. And the other big thing that we've done is we've changed this use type. So we used to use -m to m, now we're using a type extension type. So we're allowing 3 different things representing different usages. Free of voucher, obviously, means if we used it for free. None, which means if we used no voucher to buy this pizza, and buy a voucher if we use this pizza to enable a voucher, right? And we basically building this enumerated type using the voucher enumerated type, so extending that. And now we can check whether our constraint holds by saying, okay, if we look at the pizza 1, if we use that to buy a voucher, then b to the -1, which will return that voucher, and then we take f of that voucher, and that better be how we used P2. So this is the only case we're interested in. If P1 was used to buy a voucher and P2 was got for free with the same voucher, then we need this constraint to hold. And we're going to rely on the relational semantics here. If b to the -1 fails, so if P1 was not used to buy a voucher, then b to the -1 will just return undefined, and then the whole initial expression will be false, and the constraint will hold. So that's the key. We've been able to rewrite our check that 2 pizzas are talking about the same voucher. So type extension is this thing where we're allowed to add constructor functions which map one sort of type to another, to a new enumerated type. And when we do that, when we make this declaration, we automatically construct these functions f and b, and we automatically construct the deconstruction functions, which are partial, f to the -1 and b to the -1. and we add the new constants to the type, in this case none. And the advantage this has is it makes our pizza ordering programming more type safe, because now we're not using integers to represent how we use a voucher, and it makes it much more self-documented. And now let's just see why. So how does we actually implement it? Actually, we can do it all by source-to-source transformation. So basically, we can just use things which are already in MiniZinc. The use type is just an anonymous enumerator type of the right size, and the f and the b functions just map a voucher number, which gets mapped to an integer, and then back to a enumerator type use using this toEnum built-in, which has been in MiniZinc for a long time. And similarly, f to the -1 and b to the -1 use the toEnum as well. And they're partial, because toEnum is partial. Okay, we also create versions of f and b that work on sets of vouchers, which we'll use in the following models. So it's fairly easy to implement this thing straightforwardly. And why is it important? Well, we can do more things with it. So we end up often having very complex subtype usages. So here's a sort of example of a small vigorical routing problem. All right, so the kinds of objects we're reasoning about are trucks, customers, and locations. Every customer we have a location, and we have a travel time from one location to another location, and the depot is one of the locations. That's where all the trucks start. And in the typical model, we have to work out basically a grand tour of these nodes. So there's a node for each customer, and there's a start node for each truck, sort of representing where the truck starts its route, and an end node for each truck, representing where a truck ends its route. And the sort of key decisions are arrival time at each node, so we can make sure that we meet the customer's demands there, and the next node we visit after this one. So this is a typical grand tour VRP. So what I want you to concentrate on is the sort of last expression in this constraint, where we make sure that arrival times respect the travel times. So to look up a travel time, we have to say, well, if the node is a customer node, then we look up the location of that customer. So c to the -1 returns it's the customer, and then L of that is the location of that customer. Otherwise, it's a start node or an end node, and then we just know it's the depot is the location we're representing. Right? And similarly for next of n, right, it's either a customer, we look up its location, otherwise we use the depot. And so this is the travel time expression, which works out the travel time between node n and node next of n. And you see this kind of complex expression fairly often, so we've added new built-in to MiniZinc this default expression. And so x default y evaluates to x if x is defined and y otherwise. And we can use this to simplify these complex uses of subtypes. So you can see the same expression now, the travel time, we just look up L of c to the -1 of n. If that is defined, so if n is a customer node, then they'll give back the location as usual. But if it's undefined, then we just replace it by depot. And similarly for the location of next of n. And so we get a much more succinct thing, and in fact, it compiles to essentially the same code as we've written by hand. But we can compile it in a better way if we have these kind of expressions. So an array lookup of some function which might be undefined, default y, just by building a new extended array. So an expert modeler for this problem might have used this location X array, where we map each node to its location, right? So this is, if it's a customer node, of course, it's just the location of that customer, otherwise it's the depot. And then we replace that in our travel time thing by just using location X of n or location X of next of n. So that's what an expert model will do, but nicely, because this is the default expression has a very clear meaning, the compiler can automatically introduce these extended arrays for you. So we checked out how often these enumerated types or extended enumerated types appeared in the MiniZinc challenge models, and out of 15 of 129 models, we saw usages for these extended enumerated types. 64 of them could use enumerated types, so enumerated types are very powerful. And we also looked at default expressions and compiling of arrays, and we extended the compiler to automatically create that expert model, and we could see a 25% improvement in solving efficiency from the baseline if then else expression. That brings us to the end of the talk. Are there any questions?